So today we're going to look at library approaches for strong type aliases. And so essentially there's going to be two parts. First, I'm going to talk about some background. Why do we need to do this? And then obviously after that, the reason why I'm presenting this at all is because I have some proposed solutions on how we can do this, how we can create strong type aliases for our code without using any built-in compiler extensions. It's entirely a library facility. But I suppose before we go into that, then the first thing to say is, what do we mean by a strong type alias? And the basic idea of that is that you say, well, I want this type, I want it to be the same as this other type, but I want the compiler, in terms of having similar things I can do with it, but I want the compiler to say they are different types. And so we'll look at reasons for that. So obviously, there's three reasons why you might want to do that at the very basic level. The first one is for correctness, because sometimes if you have types use the same type for different things, then there can be causes for confusion, and that can lead to errors, and we don't want errors. And the second reason would be for clarity, because by giving a type a unique name, then it can make your code clearer. We know exactly what this parameter is. It's not an int, it's not a string, it's a email address, it's a port number, it's a session ID. Obviously, to some extent, we get that by just using the straightforward built-in language facilities like using or typedef, but it's easier to make mistakes when you're doing that and forget to use a typedef and just use the built-in underlying type. And of course, the compiler won't complain because it really is the same type. And then, of course, the third reason is for extensibility. So if you declare your parameter to be an int, it's an int. And if you change it from being an int, then lots of your code will need to be changed. If you want to add extra facilities to it, you can't add member functions to an int. There have to be free functions and so forth. Whereas if it is already a proper user-defined type, then adding new features to it is as easy as adding it to any other class. And so therefore, it gives you that scope for extensibility without having to change vast swathes of your code. And the reason why we want strong types rather than built-in types and library types is because these types are too common. Even hidden by typedef or using, then you can't tell the difference between an int that is a count of things, an int that is a row number, an int that is a session ID, an int that is a time. All these things, they're just an int as far as the compiler is concerned. Even if some of them have been typedef to other things. One's typedef to a time t, one's typedef to a session ID. But in all cases, it's just an int to the compiler. You can use them interchangeably, and the compiler won't complain. It's only if you've actually done something, in your code, such you can look at a code review that you can say, yes, we've got things wrong. And in addition to that, then the built-in types have a lot of implicit conversions. So you say it's an int, somebody passes you a float, the compiler says, yeah, I can change that, that's fine. Implicit convert that float to that int, sorted. Port number 3.2, probably not really what you intended, but the compiler won't complain. You might get a warning if you're lucky, but often you don't. So let's just look at some concrete examples of these particular problems. Obviously, one of them is potential confusion about the order of parameters. This first one here is standard string constructor. I want 5 zeros in my string. So I'm going to say, here's my 0 that I'm going to pass, and I want 5 of them. The compiler will merrily compile this, and it will not give you 5 zeros. it will give you a bunch of character 5. And quite how many depends on what the exact value of 0 is in your character set. If it's ASCII, UTF-8, then that's going to probably be 48. But it's not going to be what you expect. And the compiler will happily do that, even though int and char, they're different types. They both implicitly convert to the corresponding types, and you won't get a compiler error about it. Hopefully, you'll get an error in your tests because the string won't have the value that you expect it to, but it's not a concrete, it's not a compile error. And we want to get compile errors where possible. Similarly, if you've got a matrix and you're constructing it with a number of rows and a number of columns, then if they're both integers, then there's no particular way around that the compiler is going to care which way they go. Some libraries I've seen have the columns first and then the rows. Some have the rows and then the columns. And the compiler won't tell you if you get it wrong. And particularly if in lots of cases you're using square matrices for your tests, and so they've got the same, but then in reality, somebody uses a matrix which is not square, and then things go wrong. Again, hopefully you've got tests for this case, but we'd rather have a compile error than a test failure. So the next sort of issue would be confusion about the units. It might be an int. You've got a number. I've got a number of time units that I'm wishing to sleep. But what's the value of that time unit? On POSIX, then void sleep takes the number of seconds. But if you're on Windows, then sleep with a capital S takes milliseconds. And it doesn't matter if you say that my time is pause_milliseconds. If you pass it to sleep on a POSIX platform, it's going to wait that many seconds. It doesn't care that you got the units wrong. Likewise, if you've got something accelerate 2, you take a double. The parameter clearly says it's meters per second, but you think your target speed is miles per hour. Instead of accelerating to 4.3 miles per hour, you go to 4.3 meters per second, which is done so faster. That's the sort of error that caused a spaceship malfunctions, because there's one part they were using one sort of units, another part they're using different sort of units, pass the value between, all goes wrong. Alternatively, then there might be confusion over a meaning of a parameter. If I've got a socket library and I've got a socket class, I want to construct a socket, and I say, okay, well, I'm going to construct a socket that's going to listen on a port number, so I'm going to pass it the port. And then you think, well, actually, sometimes I want to import a socket that I've created somewhere else, and so I use the BSD sockets function. Give me a socket, pass it in. And then you find that, unfortunately, the value of a socket is an int, because it's a file handle, and the value of my port is, well, it's an int. Actually, if you look at the source and you find that the socket constructor for a port takes a short, because you can't have a port number more than 65536. But I pass it an int. And so then it thinks it's a file handle. And now it's not going to listen. It's going to try and talk on a socket thinking it's there. And it's got a file handle for an invalid socket. And so things will go wrong. And again, the compiler's not going to catch it. And so look at the next example here. We've got a get count function. It's going to tell us how many things there are. And because we know it's going to be a small number, and we're concerned about space, then we're going to store it in int8t, which is probably a char. And so then when we try and print out our thing, print out our count, do standard cout, there are count elements. We think we're going to get something like, there are 5, there are 15, there are 123. No. If int8 is a char, you're going to get a character represented by that count. One single character, rather than actually the count number. Because if you pass a char, you're expecting it to be a character. The library is designed around that. So you need to make sure that this is what we're actually intending to use here. Now, if you're using built-in types, then you could put a cast. You could say, no, int of my count. And the number of times I've had to do that is too many. So we want to have some solution to this problem. So then, as I mentioned at the beginning, we also have this lack of extensibility. If you use a common library type or built-in type, then the set of operations that are on it is the set of operations that apply to that library type. If there are operations there you don't want to apply, then you can't screen them out. You can't say, oh, well, you can't add to my socket number. No, it's an int. Of course you can add to it. You can't check certain other properties. You can't add member functions. If it's a built-in type, you can add obviously overloads and general free functions, but then that might interfere with the way that you would like to express your abstraction. So you can't add these domain-specific operations to things that only apply to your values. They would also then apply to anything else of the same type. People could also use that, and that might not be something that you would like. It might add confusion to your code. And related to that is you have difficulty overloading operations. And an example that came up recently was where somebody was wanting to optimize their function. They got this function that was going to do something, and they had an implementation that worked for 32 bits and an implementation that worked for 16 bits. They wanted to overload it, and they chose to try and overload it with int fast 16t and int fast 32t. And then, of course, on their platform, then because 32-bit operations are faster than 16-bit ones, also the compiler decides, then int fast 16t is the same underlying type as int fast 32t. And so then it's not an overload, it's a redefinition of the same function, and that's now an error. At least in this case, you get an error, but you'd rather have it compiled so that you could then, your code would then be portable. You could then have it compiled, work fine on one platform where that 16 and 32-bit types were different, and then compile on a separate platform where they were the same, and it would all just work without lots of if-defs all over the place. Likewise, then we have the same issue with template instantiations and specializations. If we have our class, which takes a template parameter t, then we can explicitly instantiate it for our two integer types. But of course, if they're the same integer type underlying, that is typedefs, then that is actually an error because you're duplicating the instantiation. And likewise, if you're trying to specialize your template for two different integer types, if they turn out to be the same integer type, then you've now got duplicate definitions of your specialization. And again, this is an error. So it limits portability because things that we're hoping are going to be different then turn out not to be. And then, of course, it's easy to use the wrong function. If you've got two types that really are standard strings, I've got my name type and my email type, but they're just standard strings, really, then I can call my print email function and pass in a name, and the compiler's quite happy. Hopefully my test will fail, but Again, we want compiler failures rather than test failures. We get that error sooner. This is one of the benefits of having a strongly typed language like C++ is that we have the option of compile errors. So we want our compile errors when we do something wrong. So those were the problems that we're trying to address. So what are we going to do about it? Now, before we look at that, then Connor was asked, why do we consider this C++ a strongly typed language? And I consider it to be a strongly typed language because every object has a compile time type. Whereas if you've got something like Python, which is a purely dynamically typed language, you have a variable A, you do not know what type it is at the start. It can vary its type through the running of your script. And therefore, you can't at any one type know for certain, just given the name of the variable, what type it has. Whereas in C++, then every variable has a type given to it at compile time. Now, it might be deduced type. If you've got a template parameter, it might be a polymorphic type, because you've got a pointer, and so you know that it is a derived class, but you don't know which. It might be a variant type. So the object itself has a concrete type, but you don't know which of the internal values it has. But there always is a definite type, and you know what the options are at compile time. So this is a strongly typed language rather than a weakly typed language. We want to take advantage of this when we're thinking about our solutions. So we want to create a unique, distinct type for every single usage for our and in order to avoid all the problems that we've been discussing so far. Now, this is the whole value idiom. The whole value of something is not just the internal value of the variable, but also the type of the variable, what units it has, any other context that goes with it. And we want to encode as much of that as possible in the C++ type system. If we have a price that's £4.32, then it's important that that is British pounds and not dollars or yen, or lira. It's important that the currency is part of the type. Likewise, if we have a distance, 27.6 kilometers, now that kilometers is important. 27.6 kilometers is quite different from 27.6 meters or 27.6 light years. And so if your code has distances in other units, it's important to say this one is in kilometers. And even if it doesn't, then actually from a usability point of view, from somebody who's reading the code, it's nice to be able to make it clear that this is a distance in kilometers. And likewise, it can be important that Anthony, as a text string, is not just any old text string, it's a name. Because there might be certain things you wish to do with those names. It might be important how they're displayed. Or it might just be that you need to make sure that certain names go in certain types of storage, and whereas other things go somewhere else, or even just for correctness. This is the name field, so it needs to go in. It needs to be a name and not an email address. And likewise, Anthony@justsoftwaresolutions.co.uk is an email address, and that might be important. It might be that you're going to turn that into a hyperlink, stick mail to on the front, so that somebody can click on it. And so the type of the string affects its usage. And so we want to encode that in the type system. Now, obviously, the obvious basic way to do it is you can create a class. So we haven't got a length that's a double value. We have a length in meters. It's an outstruct. Obviously, it is now quite distinct from all other doubles. It is distinct from a length in kilometers, which we could create as another class. But just as it stands as an empty struct, the operations you can do with it are pretty minimal. So you can get the value out. You can call, if you have a length L that is one of these length in meters, you can say L.value, and that will give you the value. And then you can then do all the operations you would do on the double, because you've got the double out. But from passing it around point of view, then you can copy it, you can create it with basic visualization, but that's about it. So if you want to add any operations to it that don't just break the encapsulation and give you raw access to the underlying value, then you're going to have to write those as operators or member functions or free functions in order to do that, provide that operation. If you want to add to lengths in meters and get a new length in meters, you have to write an overload of operator plus. And if you want to do the same for your lengths in kilometers, then you have to write another overload of operator plus. And if you want to be able to add a length in meters to a length in kilometers, then you need yet another overload. And you need to decide what value you're getting from your operations as you add them. If we find that there's a lot of things that are in the same domain, we have a lot of lengths that are different units, or we have a lot of times of different units, then we might create a template. The standard library does this for us. Standard duration. We can say, well, I want a duration, and I want it in nanoseconds, and I want it only to store short values. And so if we do this, then we can the template library then says, okay, well, I know it's now a duration. You can pass it around. It's convertible to other durations, and it will do the automatic scaling. And if there is a scaling and it says, well, actually, I know that I can't store all of the values that you want in that. No, I've got a value in seconds, and I try and convert it into a short number of nanoseconds. I know that sometimes that's not going to fit. If I've got anything other than 0, 1 second is a billion nanoseconds. That's not going to fit in a short on most platforms. So the compiler will actually know to make that an error. Whereas if you say, I've got a number of nanoseconds stored in a short, and I want to convert that to the number of nanoseconds stored in a long, that's fine. Or if I've got a number of seconds stored in a short, and I want to convert that to nanoseconds stored in a 64-bit value, then yeah, I can do that. It's going to be a lot of nanoseconds, but it's doable, and the compiler deals with that for us. And then obviously you can add durations, you can subtract durations, you can divide them by a constant and get more duration, but you can't multiply two durations, because what would that be? Time squared. The standard library doesn't have an option for that. But we could write our own library. We could get an SI units library. So we have a length type. We say it's kilometers. We have a name. We could also then have use that with our duration and define templated operations on length and duration. So we have a distance in kilometers. We divide it by a time in hours. We get a speed in kilometers per hour. And we can do all the appropriate domain operations. There are many SI units libraries out there which allow us to do this in C++, where each type has its own, each basic unit has its own type, and then when you multiply them together, you get a compound unit. So you can have speeds in meters per second, you can have accelerations, you can have forces, and these naturally come by multiplying and dividing the appropriate basic units. So if you have a domain for your values, so you've got lots of discrete things which have the same sort of properties, then a single template for that domain makes a great deal of sense. but not all values that we might deal with seem to fit in that sort of thing. No, names are, well, they're names. There's not really much that we might want to say about that. No. Likewise, an email address, well, it doesn't have ever so much in common with other text strings. No. Numeric IDs, well, you might want to have a general sort of ID template, but a session ID is not really anything to do with a row ID or a concert ticket ID or somebody's driving license ID. Or if we've got row and column counts, then for our matrix, we say, well, we've got row numbers and column numbers. Then we can create distinct types for those so that we don't have confusion over our constructor parameters. But there's not necessarily much that we would want to do with them that they would have in common with other numeric things. But then again, there might be some things that are in common. We might want to use our names, we want to be able to sort our list of names, so they need to be comparable. But you might also want to be able to sort your list of email addresses, so they are too comparable. And so now you've got two string-based things which have the same operations, but they're not related. So we need to look at that and think about how that's going to impact what we're doing for our generation of these strong types. So yeah, some examples of common operations that we might have. And if you've got numeric values, you might want to do arithmetic operations on them, but you might want to limit what they are. You might want to say, well, this is a number, like a length. So I can add two lengths, I can subtract two lengths, but I can multiply them by constants. But then 3 times a length is just a length, but 2 lengths multiplied by together is not a length anymore. So we want to be able to encode that in our operations. But we might have other things that we want to be able, times you can add together, and things like that. Counts you can add up, but you wouldn't necessarily want to be able to divide things. And so you want subsets of arithmetic operations. Something that's a bit field, you might not want to add, but you might want to do bit operations. And if that was a plain int, then both would be allowed. But if you define it as a strong type, then you can say, I want bit field operations for this, or I want arithmetic operations. In lots of cases, we want stream output, whether that's for logging, for displaying on the screen, for actually writing to disk files, for writing to the database storage, whatever, sending over a network. Often want to stream out our values. So we're going to need stream operations. And in many cases where the type of the data is clear from the surrounding context, then that stream operation can just write the underlying value, but it might not. You might want to encode the value in the stream output. You might want to add additional data before or afterwards. So writing the value in kilometers, you want to put 5 kilometers, so that value is there. Alternatively, you might say length in kilometers. There's a parameter already, so you just say 5. Like I said, if you're wanting to sort lists, you might want to be able to do ordering. You naturally might want to do equality, even for something which you wouldn't otherwise care about. It's like, well, is this the same value as that one? They don't have a necessary order, but I want to know if they're the same. If you want to use them as a key in an unordered map, you might need to hash the value. You might want to convert to a string for the same reasons that we might want stream output. Converting to a string is, say, you could use standard string stream and write to that, but there might be a more direct canonical way of doing it, and so conversion to a string there might be something you might want to do. And then you might want to add some certain user-defined conversions. You might want to be able to convert to the underlying type in some instances. You might be able to want to convert to other things, so like nanosecond durations convert to second durations, or millisecond durations. Length in meters converts to length in kilometers, that sort of thing. And so these are things you might want to add, and you want a nice framework for doing that. And the thing is, if we try and do this every time, then we end up with a lot of boilerplate operations. We've defined our addition operators for length for every different type of length. So, and then we've done, okay, so we templated out that. We've done a template for lengths, but then we look at our template for durations and find that it's the same set of operations we're doing, but we've just substituted the word length with the word duration. And that's duplicates. That's a waste. That's boilerplate. We don't want to do that. And in C++, there are fundamentally two ways that we get away with this duplication. One is to use macros, and one is to use templates. From where I sit, macros are horrid and something to be avoided at all costs. And so that leaves us with templates. So what can we do as a template to make our strong types? So ideally, I want to be able to declare my strong type as simply as possible. I want to say, my type is a strong type of something. And the more I have to type in the something, the less happy I am. Because the quicker it is, the easier it is to write your own custom type. So how do we do that? What can we do to make it minimal? Well, we want to be able to have something that can tag this to say it's a unique type. And so my library, we introduced the first type of template parameter is a tag. It's not used for anything. It doesn't matter if it's incomplete. If you declare it right there as a struct my type tag, then you're not going to use it for anything else because you've just declared it here. And it is implicitly created. It's neatly sits in. You have to watch for which namespace it ends up in, because if you have similarly named things in different scopes, then you can find that if they're nested classes and things, then they might end up in the enclosing namespace, and you need to be aware of that. But fundamentally, you create this type, you give it a nice name, and it's now a unique tag that says this is a different type. And then you want to say what the underlying type is. And if that's all you're doing, if you're wanting to create a unique type for this int is different to all other ints, then that's all you need to specify. And that is comparable, but not as short as just saying struct my type has an int in it as a value, but it possibly a little bit clearer because then it is a nice unique type and it's easily extensible. We've got a question about using static reflection and whether that's a viable option to templates and macros. I think that, yes, static reflection would be a good way of doing things. Obviously, it depends on quite what the syntax ends up looking like as to whether it is clearer than essentially writing out a template. If we're allowed to define essentially new keywords, so we could make strong type def a keyword because using the static reflection properties, then that would certainly make it have a scope for making the actual the syntax that we're writing that much clearer. It's possible that, yes, we could use static reflection to remove duplication of boilerplate. And so there's plenty of scope there. I haven't looked at the proposals enough to know quite how that would be and what it would end up looking like. But I think there's certainly there's scope for it being so. So obviously, one of the reasons why we're going looking for our template library is because we want to have more than things that just are, well, it's a bit like an int, but it's a new type, because we could have done that with an empty struct, with a simple struct with just one value. So we need to know what else we're going to do. So firstly, we want to make it explicitly constructible from the underlying type. So if we base it on an int, then we want to say my type of 42. And equally importantly, if we just have a 42 and our parameter is a my type, we don't want it to compile. No. We do get that if we just have a plain struct, except you'd have to put the curly braces in rather than parentheses. But again, we're after additional operations, why we're using a template rather than just a plain struct. So this is where the additional arguments for our template come in. And so the idea within the library that I've written is that you add additional operations by adding these additional template parameters. It's an open-ended list. You say, I want my types to be addable. And there we are, they're addable. I want them to be equality comparable. It will add the appropriate operator overloading. And it's just a variate template parameter, so you can add additional properties. There's a quite long list in the library, and then of course you can add your own. We can, of course, always access the underlying value. Just like if you had a plain struct with a value member, you could always access the value member. But we want to make it a bit harder. We want to make it clear that I am retrieving the value from my typedef. So I've given it this long-winded name of underlying value. It's also not something that's likely to clash with any other operations that you choose to add. If you're adding member functions, then there's not going to be many that are called underlying value, whereas something called value is much more likely to come into conflict. And then see underlying value returns a reference. So once you've fished that out, then yes, you can update the internal value and do any of the operations you normally can on the underlying type. So again, this is something you want to stand out. It's like a cast. You want to make it clear. I'm doing something a little bit funny here. So make it easily grabbable. By default, then conversion is explicit only. So you can do a static cast to get the underlying value, but you can't do an implicit conversion. Obviously, if you wish to change that, you can add a property to do so. But by default, then we have this, you have to do the cast. And so this is, we have our strong typedef template. It can provide these basic operations just built in there as members of the template. Somewhere we're going to get some base classes. Those are going to come from our properties. But other than those, then we have our default constructor. We have a constructor, an explicit constructor taking the value. So no implicit conversions in. We have an explicit operator providing the value. So no explicit conversions out. The implicit conversions go the other way. And then we have constant, non-const access to the underlying value. So it's very simple in the base case. It's essentially like our basic struct, but with a few more constraints on there to give us a little bit more safety and potentially usability. So then what about these properties? Well, all the properties are structs with a mixin member, which is itself a template. And the mixin template takes two parameters. It takes the final derived type, which will be your strong type def, whatever, instantiation, and then the value type, which is the underlying type of it. In theory, you could deduce the value type from the strong type def template, but in practice, I found that it made a simpler code if you just explicitly passed it as a parameter to the mixin. And then, so this example is pre-incrementable. So it's the same, we want to provide a pre-increment operator. So we do just that. Declare a friend operator that works on the derived type. It is no except if pre-incrementing the underlying type is no except. And it just does that. It takes the derived type as a parameter, which we've called self. It increments the underlying value, and then it returns that parameter. So this doesn't care what our underlying value is. It could be an int, it could be an iterator. Anything that is pre-incrementable as the underlying value can now be pre-incrementable as a strong type def. And so the way we integrate those to create our strong type def values is we publicly derive from all our mixins. So we do a plaque expansion of the mixins members of all our properties. And again, we pass in our the full type name of our strong type def, with its tag, its value type, and its properties expansion, and the value type again. And then obviously, and that will then expand. For each property, it will instantiate the mixin template. And they will all become the base classes. And so our type def will have as many base classes as it has named properties. And then, of course, it has the basic members that we saw on the previous slide. So the way that you have your fine-grained we add the properties means that they can be as fine-grained as you like. So you can specify that my properties are, my session ID is post-incrementable, but not pre-incrementable because I didn't ask for that. Equality comparable, and I'm going to say ordered and streamable, but nothing else. So other operations that you might be able to do on unsigned long gone are forbidden. But if you have to spell out all these operations, then that's going to get very tedious. And given that, again, there's going to be lots of things. Lots of the times we've got an ID. We want our ID to be comparable. We want it to be hashable. We might want it to be incrementable, and we might want it to be streamable, and all these things. But so you want to be able to combine properties and say, well, this type has this bunch of properties that I defined. And so you can just do that. You can create another type, another mixin that just itself derives from all the individual mixins that you want to combine. And so if it's comparable, just as a general thing, then it's also ordered and equality comparable. And if you want to have something that was had all the arithmetic operations, then it could be addable and subtractable and something you can multiply and something you can divide, and or you might have a class for all the bitwise operations, which then combines each of those each of the mixins for the things then becomes gives you a combined mixin. Hashing is a funny one because standard hash doesn't have any extension points. The only way you can extend it is by specializing standard hash. And specializing means that you can limited on how you can do that. You can specialize for strong typedef because it's a user-defined template, but you can't specialize easily for strong typedef with some properties. So even though we only want to work where the user has explicitly requested hashable, it's very hard to say, do a concrete specialization of the whole standard hash class for strong typedefs that specify hashable, because you can't, the partial writing that partial specialization would be too tricky. Particularly if you're trying to deal with combined things. So you want to have a combined property that allows hashable and streamable and comparable, and well, now that would break any specialization that we had, because the declaration of the hashable property is now buried as a base class of one of the combiners. So instead, we add a new base class, in this case an empty struct, which is a member of our hashable property. And our mixin just derives from that. We're not looking to add any operators or friend functions here, so we don't need to do anything special. And then we can do our general specialization of the standard hash. So we can just specialize for any strong typedef. So any strong typedef that now has a specialization of standard hash. But we can use enable if to check where the base class is somewhere we have a hashable base. And that way, then, yes, there's a specialization, but if you haven't explicitly requested hashable as one of your properties, then there won't actually be an operator, parenthesis, function call operator, so it won't be usable as a hash function. The operate details is then a bit more complicated. Again, it's mostly we have if hashing the underlying type would be no except, then hashing this type is no except, and then we just hash the underlying type. So it's a little bit complicated, but when you break it down, it's quite simple. So if you've got a C++ 20 compiler, then you can replace that enable if with a concept. And that might make it read a bit simpler and allow the allow the compiler to optimize things a little bit better, perhaps, or parse it a bit easier and give you better error messages. Let's see. People are commenting on chat about the use of enum classes for integrals, and yes, I think if you just need a simple operation on an integer which doesn't have much in the way of operations, then an enum class works well. I've in the past used them very successfully for bit fields. We've done presentations on that sort of thing before. But as soon as you want to do additional operations, then suddenly they're a bit clunky and they don't work as well as you'd like, you know, and so they are more limited than a general template. So yes, Peter's going to do a talk about that, he says. So yeah, if you want to learn about enum types, then watch Peter's talk. So what if you want to do a custom property? Well, custom properties are really straightforward. You know, I've already shown you how to do that sort of thing. You know, in the previous slides, you know, you've got the library provides things for most of the operators, but you can easily define your own property type to add additional things. You can have member functions, you know, whereas operators tend to do free functions. If you do your own property type, then you might want to add member functions, and that works fine too, because these mix-ins perform base classes. Then any member functions that you provide, they're public base classes, so public member functions are automatically available. So if we wanted to do a property that said, well, it's a string-based type, so I want to provide the C-str and substr operations because I know that I'm going to want to pass it to some C-based APIs. And I want to be able to take substrings for some purpose. And so you just declare your mixin, which has member functions. So we have a nice member function here, C-str, which just casts our this parameter to the most derived type so we can get its underlying value, and then calls .cstr. And likewise, now our substr, we're going to do our cast to the most derived type, get the underlying value, call our substr operation, and then wrap the whole thing in a derived so that our substring is still an instance of our strong type. Now, we're not losing any encapsulation by providing this substring operation. We are explicitly wrapping things up. And so this is then safer from the user's perspective than calling substr on the underlying value directly. And it allows us to put control over that. And you could even have the return value be a new strong type def, which therefore has a different set of properties. If you're doing things like division, then very often if you divide a time by a time, well, that gives you a unit list number. But if you divide a length by a time, then you get a speed. And so by putting the member functions in, then you can have control over what the return type is and make it something that maintains the type safety that you're striving for. So here are some example uses that look like the sort of things that I've actually used in real code. We have session IDs. They're based on unsigned long, so this application's generating session IDs. It can run for a long time. They're not going to wrap round. We don't have to worry about cycles and things. But we want them to be incrementable and comparable and streamable and hashable, but we don't want any other arithmetic operations. See, got my D's and P's confused. I'm trying to do strong type def, reduce the properties thing. So yeah, obviously in my library, then strong type def properties is a long name. And so in practice, then you might want to put a using namespace somewhere. And then we can use our session IDs as keys in containers because they're comparable and they're hashable. We can write them out to a stream, and we can increment them, but we can't just add 5. We can't subtract 6. We can't subtract them from each other. There's a general use case. You would have one instance that is a monotonically increasing source of these values. I've got my next ID, say ++ next ID, and then I've got a new ID value that I can use. And when somebody else comes, they say ++ next ID, and you never go backwards. So it's always clear that this is just an increasing session ID count. And then we might have usernames. Usernames, again, they're strings. And they're streamable, they're comparable, they're hashable. But you can't increment a username. You probably don't want to add things to it, so we're not going to make them addable. You can't. We don't want to concatenate strings to make our username. The user enters it as is, so we're not doing anything with it. We can compare them to others, but the relative ordering doesn't necessarily mean anything other than being useful as a key. But we don't necessarily have any other operations on them. And then, right at the minimal extreme, a password. Well, a password is a string, but we don't want to compare raw passwords. We don't want to hash raw passwords with standard hash. You might well have a password hashing operation there. Something that does a SHA-256 or something, or a nice secure password hashing algorithm that does repeated loops and things. But generally, you're not going to want to write out a password to a stream because that would be a security leak. We don't want to be able to directly compare passwords because we want to compare the hash. So we don't actually limit the operations we can do on our password operation, on our password type. So we are really, really minimum. And then the compilable tells, we're trying to do something, that we're trying to print a password on the screen. Well, do you really want to do that? No. All these things. Then the compiler and the type system will now help us, making sure that we're doing the operations that we want to do. And obviously, by using these strong typedefs, then if we decide that actually what we really want is a custom class, then it's trivial to convert your typedef into a custom class because it's already a unique type that you might get from a custom class. And so we're not having to worry about anything breaking just from that. If our custom class provides exactly the same operations that we've specified, then we know that things won't break because there aren't any additional operations. Everything that takes a username, well, it takes a username. It doesn't take a string. It won't sometimes take a string and sometimes take a username and hope that they all work because it's a strong typedef. Then everywhere will take username. And so we change that to a class, and now, yes, things will need recompiling. Oh dear, we've broken ABI. But you can. It's your application. You can recompile it at whim, and then you can add operations that are now specific to your username class. And it provides a nice forward evolution route. So one thing that I will say is that when you're debugging these, if you're using GDB, then it has a tendency to display empty base classes. And if you've got a lot of custom properties, that ends up with a lot of empty base classes, each of which has has a template parameter, which is the full instantiation of your strong typedef. And you can end up with a great big list of empty base classes. You might end up with a 15-line printout of empty base classes just so it can say value equals 42 at the bottom. So GDB has this nice thing where you can write custom pretty printer features, and so if you actually look in the source code for my library for this, which is on GitHub, then there is a Python GDB pretty printer for the strong typedefs that will just print you what the value is. So it'll say value equals 42 rather than printing all these empty base classes. And if you're using a different debugger, then the GDB one won't work. But if you have the same problem, then it might be worth adding a Visual Studio debugger custom printer or something. They're a bit more fiddly when I looked at them last, but you can do them. So yeah, so there's a comment on chat. Each of those template parameters adds to the namespaces considered for the ADL. Yes, but see, depends what you do with your template parameters. If all your custom properties come from the same namespace, then that's not really had much of an impact. If you've written custom properties all over the place, then yes, you've added extra namespaces. But if you've got reasonable namespace hygiene in your code, so it is clear, the things in the namespace go together, then if you've included a custom property from a namespace, then yes, it will pick up the operations from there, but that's because you wanted it to. So yes, it's something to be aware of, but hopefully it's not going to actually cause you a big deal. Okay, so here are some links. So the library that is the focus of this talk is my JSS Strong Typedef library. That's the GitHub link at the top. Peter Summerad's library that he discussed in his talk earlier. Here's the second link there. Martin Mona's whole value library. Now this one uses macros, but it does allow you to declare things as whole values. It also has limited sets on the operations, so you might find it simpler if that's what you want to use. But when I was having a look at it, it seemed less flexible. If you've got things like SI units, then you might want to look at the bottom two. Boost units and MP units are SI units libraries. And they allow you to say, this is a length, this is a speed, this is a time. Speed times time gives us a distance, and all that sort of thing. So, if what you're wanting is specifically something that would be mapped to an SI unit type thing, then those might work well for you because they naturally provide all the combining and scaling operations. And yes, Peter says separating strong types and unit types is important. And yes, quite possibly. It might be as well to say, yeah, this is a length in meters. But what does that mean? Is that a length in meters that represents the height of a building? Is it length in meters that represents the stride of a man? Is it the length in meters that represents the world record long jump? You wouldn't want to confuse these, and so you might actually therefore want to combine your SI unit library and use that as the underlying type for a strong typedef. So I'm not going to do a talk without plugging my book. It's concurrency, C++ concurrency in action. It's written to cover C++ 17, but there is going to be a C++ 20 addendum coming soon, which will be a free download for anyone who's already bought the book. And that leaves us plenty of time if anyone's got any more questions. So yes, somebody's straight in there with a new question. And it says, have you considered other ways of making unwrapping stand out other than the long method name? I imagine using something like this for wrapping types while directly using old APIs with a function call operator or something. With underlying value wrapping APIs themselves in a facade as well seems like the only reasonable option. So yes, and that depends what you're trying to achieve. The library that I've got. So yes, there's a long method name as a member function. There's also a free function with the same name, so you can call that actually works on. If it isn't a strong type def and you ask for its underlying value, it just gives you the value back again. It's the identity operation. But yes, generally, if you're looking at doing operations on things, then I would say that actually you don't want it to stand out in lots of the cases. What you're wanting is for your operation to be clear, and so you're writing the I want to do this operation on this thing, and your thing will be a strong type def instance, and then the operation will just be overloaded or something to take a strong type def instance. Alternatively, then your strong type def instance might have a custom property which allows it to implicitly convert to the right type for your operation. And that I find that usually you only want to call something out where you're breaking that encapsulation, and the use of just underlying value actually, in my experience, is enough. It highlights it as this is something odd's going on here, like static cast or a const cast. You can grep for it, and it's enough to make it highlight. And when you don't want to, if you find that you're highlighting it in too many places, or I'm calling underlying value everywhere, well, what's the operations that you're trying to do? Can we add those? Can we add overloads to our, to take the strong type as a parameter? Can we add a conversion to the type? I think if you're wanting it to stand out more, then that feels like the wrong way to be going, actually. And like I say, I've used this. I use this all the time. I think pretty much every time that I'm creating a new class for some purpose, then I find there's something somewhere in there where I'm going to want some parameters, and well, it naturally feels like it ought to. It's an int, but it's not just any old int. So I'm going to give it a name and a strong type def. So this is something I use every day. There's something like, and I find that it makes your code simpler. And so I hope that you find it makes your code simpler as well.